VinFuture Prize, a new global science and technology prize for humanity from Vietnam. One VinFuture Grand Prize of $3 million. 3 additional special VinFuture prizes valued at $500,000 each. VinFuture Prize honors science and technology work that creates or has a high potential to create meaningful change in the everyday lives of millions of people. Join us to make a change for a better future.
Warmly welcome our distinguished speakers and colleagues joining us from around the world. On behalf of the VinFuture Foundation, I'm delighted to welcome you to the first InnovaTalk webinar of 2026. My name is Lina, and it's my pleasure to be your moderator today. Today's session explores one of the most transformative frontiers in technology, the rapid evolution of artificial intelligence. As AI systems invest beyond task-specific tools towards autonomous agent-based architectures capable of planning, adaptive reasoning, and dynamic interaction, they are reshaping how humans and machines collaborate across complex environments. In this context, the VinFuture Foundation is collaborating with the MIT Computer Science and Artificial Intelligence Laboratory to host the InnovaTalk title, Next Generation AI in the Era of Autonomous Agents. We'd like to extend our sincere thanks to the MIT Computer Science and Artificial Intelligence Laboratory for partnering with us on this meaningful discussion. Together, we will explore the latest development in AI, autonomous AI, and the opportunities they unlock across the industry and society, and the critical challenges surrounding reliability and human oversight. And now, it's our pleasure to introduce our chair of today's webinar, Professor Daniela Rus, member of the VinFuture Prize Council, Massachusetts Institute of Technology. The webinar also welcomes 3 distinguished speakers: Professor Antonio Torralba, Massachusetts Institute of Technology. Please welcome Professor Vijay Kumar, University of Pennsylvania. Joining them on the panel as a special guest is Associate Professor Minh-Triet Tran, University of Science, Vietnam National University, Ho Chi Minh City. To set the tone for today's discussion, let's take a moment to watch a short video that highlights the key theme we'll be exploring together.
Amid the accelerating evolution of artificial intelligence, the field is undergoing a decisive shift from task-specific systems toward autonomous, agent-based architectures capable of planning, adaptive reasoning, and dynamic interaction within complex environments. While these advances promise unprecedented efficiency and scalability, they simultaneously sharpen critical questions of reliability, governance, and the evolving scope of human oversight in high-impact domains. In this context, the VinFuture Foundation, in collaboration with the MIT Computer Science and Artificial Intelligence Laboratory, USA, will convene the InnovaTalk webinar titled Next Generation AI and the Era of Autonomous Agents. The session will bring together leading interdisciplinary perspectives to examine the development, deployment, and global implications of autonomous AI. The webinar will be chaired by Professor Daniela Rus, member of the VinFuture Prize Council and MIT Panasonic Professor of Computer Science at the Massachusetts Institute of Technology, where she directs Computer Science and Artificial Intelligence Laboratory. She is also a member of the U.S. National Academy of Engineering, the National Academy of Sciences, and the American Academy of Arts and Sciences. Beyond academia, she is a co-founder and board member of Liquid AI, Themis AI, and Venti Technologies. Throughout her distinguished career, she has received numerous prestigious honors, such as the Engelberger Award for Robotics 2017, the John Scott Medal 2024, and the IEEE Edison Medal 2025. Joining her on the panel is Professor Antonio Torralba from the Massachusetts Institute of Technology. He is currently the Delta Electronics Professor and head of the AI Plus D faculty in the Department of Electrical Engineering and Computer Science at MIT. Through his work, he has advanced the understanding of neural networks, large-scale image databases, helping shape how machines interpret and interact with the visual world. His outstanding contributions have been widely recognized with prestigious honors, including the NSF Career Award 2008, the PAMI Mark Everingham Prize 2020, and the Thomas Huang Memorial Prize 2021. Our next distinguished speaker is Professor Vijay Kumar from the University of Pennsylvania. He currently serves as the Nemirovsky Family Dean of Penn Engineering at the University of Pennsylvania, with appointments across mechanical engineering and applied mechanics, computer and information science, and electrical and systems engineering. He is a fellow of ASME and IEEE and a member of the U.S. National Academy of Engineering, the American Philosophical Society, and the American Academy of Arts and Sciences. Beyond academia, he is the founder of Exyn Technologies, an advisor to TreeSwift, and serves on the boards of Robotics and O2 Micro. Last but not least, the webinar is honored to welcome the special guest from Vietnam, Associate Professor Minh-Triet Tran, Vice President of the University of Science, Vietnam National University, Ho Chi Minh City. Associate Professor Tran earned his bachelor degree, master degree, and doctor degree in computer science from the University of Science, Vietnam National University, Ho Chi Minh City, and has been a faculty member since 2001. He has also been a visiting scholar at the National Institute of Informatics Japan and the University of Illinois at Urbana-Champaign, USA. He has contributed significantly to the global research community through leadership roles in major conferences, including General Co-Chair of MMM 2022 and MMM 2027, and as a member of the organizing committee of ACM Multimedia 2025. Join us at the 2026 VinFuture InnovaTalk webinar, Next Generation AI and the Era of Autonomous Agents.
These are major highlights we discussed shortly. And now it's my great pleasure to introduce our esteemed chair. Please join me in giving a warm virtual welcome to Professor Daniela Rus, member of the VinFuture Prize Council, Massachusetts Institute of Technology. Professor Rus, the floor is yours.
Thank you so much for this wonderful introduction. Good evening in the US. Good morning to our colleagues joining from Vietnam and across Asia. I'm Daniela Rus, Director of MIT's Computer Science and Artificial Intelligence Laboratory, and also a member of the VinFuture Prize Council. And I'd like to welcome you tonight to a very important conversation. And I have to say, it's wonderful to be here with such a wide and international audience, because one of the most powerful aspects of AI right now is that it is a global technology developed through the global research communities and shaped by diverse cultures and values, and increasingly deployed in settings that look very different from the technology hubs where many systems are first created. Now, we are living through a remarkable moment in artificial intelligence. In just the past 2 years, we have seen AI systems make leaps that many of us expected would take much, much longer. We've seen models learn to reason in increasingly sophisticated ways. We've seen models plan multi-step sequences, write and debug code. We've seen models that interface with tools and data sources. And we've seen systems that can summarize scientific papers, draft legal language, design software, or help diagnose disease. And we started to see AI not only as a predictor, as something that classifies or recommends, but also as an actor, a system that can take steps, make decisions, and pursue goals over time. And this shift from models that respond and predict to models that act is what today's conversation is really about. Now, when we talk about autonomous agents, we're talking about systems that can take a high-level goal and translate it into a sequence of actions. And these actions involve planning, calling tools, retrieving information, asking for clarification, taking intermediate steps, adapting based on feedback. These systems are beginning to look less like single-shot applications and more like software entities and physical entities like robots that can operate across time and interact with other systems and even coordinate with one another. We're also seeing the boundaries between digital intelligence and physical intelligence, that means intelligence in the physical world, begin to blur. Foundation models are now being adapted not only for text and images, but also for control, for robotics, for embodied decision making. We have robots that can learn from human demonstrations that show how humans do tasks that cannot be modeled from first principles. We have robots manipulate objects with increasing dexterity and operate in spaces designed for people. We have seen the emerging world models that attempt to capture how the world changes so that an AI system can anticipate what happens next and choose actions accordingly. And in the lab, we're seeing robots that can do tasks that used to be too complex or too variable. We have warehouse picking robots, we have assisted mobility, inspection in hazardous environments, and increasingly nuanced forms of human-robot collaboration. And the pace of advancement and of change is extraordinary. But speed also raises some hard questions that we have to start addressing right now, that we cannot postpone until later, because the technology is already here. And so some of these questions involve answering, how do we govern systems that can act autonomously? What do we allow them to do? What do we prevent them from doing without human oversight? How do we build reliability and safety into systems that learn from data and may behave in unexpected ways in edge cases? And how do we ensure that these technologies are aligned with human societies and with the good in the world, not the evil in the world? So these are all questions that matter to us deeply. And when I think about this topic, I like to frame our conversation around three themes. The first theme is capability. And here we ask, what can autonomous agents actually do today? And what will they likely be able to do soon? What are the technical ingredients that are driving progress on the data side, on the hardware side, on the algorithm side, on the AI architectures? And are there ways to integrate models with tools and environments? The second piece is trust. How do we build systems that are reliable, safe, secure, and support human values? And what do we need in terms of evaluation, verification, monitoring, and human oversight? And how do we make these systems robust in the real physical world where conditions are noisy and unpredictable? And the third piece is impact. How do we translate breakthroughs into broad societal benefits? What kind of investments are needed in research, in infrastructure, in education, in policy, so that autonomous AI becomes a force for human flourishing? And these are exactly the kinds of questions that we at CSAIL explore, and also the VinFuture Prize is evaluating. So these are the topics that we are going to discuss today, and we will explore questions around how we build AI systems. What are the most promising architectures? How do we evaluate reliability? And how should we cooperate internationally in order to ensure that AI advances the knowledge and also supports humanity and our planet? Now, I would like to end with one thought that I've found very useful. In the history of technology, the most transformative systems are often the ones that become infrastructure, so normal that we stop noticing them. In fact, just think about electricity, think about water, think about internet. When they work well, they fade into the background and enable better lives. And so my hope is that we will build autonomous AI in the same spirit, as systems that become part of the fabric of life, systems that are reliable, safe, and broadly beneficial. Technology that expands human capability rather than replaces human judgment. And systems that help us solve grand challenges and problems that matter, from health to climate and education and everything in between. Now, this is our big ambition, but it's a right ambition. And with that, I'm delighted to welcome our first speaker. Vijay Kumar, the floor is yours.
Such an amazing topic. Thank you, Professor Rus, for setting the stage for today's discussion. We now turn to our first distinguished speaker, Professor Vijay Kumar, University of Pennsylvania. Professor Vijay Kumar, we look forward to hearing your insights.
Thank you for inviting me to speak and share my thoughts about the excitement surrounding robotics and physical AI, both the hype and the reality. I'm Vijay Kumar. I'm the Dean of Engineering at the University of Pennsylvania, and I've been working in the field of robotics for over 3 decades. Today's state of the art in robotics can be summarized by these pictures that you see, these 4 scenarios. On the left, top left, you see the Ford assembly plant. This is an example of scripted motion. Robots are pre-programmed completely. They require static environments and well-specified tasks to function. Of course, you get high accuracy and high repeatability, and this results in 24/7 automation, high throughput productivity, and this is essential to today's manufacturing. On the top right, you see a picture from Amazon robots doing intelligent pick and place. Robots can identify items in various positions and orientations and pick them up for sorting. Now you see the beginnings of generalizable perception, some generalizable grasping, and pick and place for a limited class of robots. On the bottom left, you see autonomous mobility for legged robots on uneven terrain. Robots can understand the open world, navigate and traverse different terrains, and you can see advances in high-level planning, spatial reasoning, and some robust locomotion emerging. On the bottom right, one of the first humanoid deployments in factories. This is from Agility Robotics. They're on the shop performing simple pick and place tasks alongside humans. The key is they can do function in the same environments that humans can function. What is physical AI? Well, there's a 2025 World Economic Forum report that highlights the need to embed a new AI technology stack into robotic systems. The idea is to create AI systems that can sense, reason, and function in the real world, taking autonomous actions. It also allows robots, in theory, to adapt to the environment and the specific mission and to go beyond simply following a scripted plan. A big part of this, of course, is the use of ML systems as part of the feedback loop. And we're already seeing this play out in self-driving cars. Companies like Tesla, Waymo, and Zoox are leading the development and deployment in the US. And there are many more companies in China: Baidu, Pony.ai, WeRide, AutoX, XPeng, BYD, and Huawei. The list goes on and on. Much of this industry is designed and driven by data collected by humans driving many billions of miles. And from that data, they can actually automate driving to some extent. Companies like Waymo leverage simulation frameworks that allow them to multiply real-world miles by factors of 1,000 to 10,000 for scenario edge case training. And they produce virtual data equivalent to hundreds and billions of miles analyzed. So if you look at this industry and physical AI in general, there are 3 macro trends that we can see. On the right, I show you examples of some of the robots that we use in my lab, using custom hardware which we develop, and some with integration of the off-the-shelf hardware. So the three major drivers are listed here. Steady decline in price to performance ratio sensors and processors. If you look at NVIDIA GPUs is measured in terms of dollars per trillion operations per second. Ouster LiDAR is measured in dollars per range and resolution. Vision system measured by dollars per megapixel. There's a steady drop, which bodes well for the field of robotics. Similar trend in actuators and materials. The Tesla Optimus robot is built with lightweight materials and actuators with a very impressive strength to weight ratio. The second trend is this paradigm shift from model-based approaches to data-driven approaches. Self-supervised learning at scale, for example, in speech, text, and vision, where internet-scale data has enabled VLMs, LLMs at a scale that nobody anticipated even 5 years ago. The third trend we see is the sim-to-real gap, which is steadily shrinking. Simulation tools are getting more powerful. The use of large-scale compute with techniques like domain randomization have enabled walking on unknown terrain with different material properties like friction, and of course, self-driving cars. So in my own lab, we use drones like these, which are now able to navigate unknown environments without GPS and without human commands. We use onboard sensors like cameras, LiDARs, and processors, standard sensors and processors like Intel GPUs and NVIDIA GPUs to cover a square kilometer of area in 30 minutes with localization to within 20 centimeters. I want to show you some examples from precision forestry. This is our drone flying through pine forests nearby in the state of New Jersey. They're able to navigate environments like this and cover in 30 minutes, they can cover about 1 square kilometer. They count trees with estimates of diameter at breast height to within 25 centimeters. And this is useful information as we think about industries like timber harvesting, and of course, for estimating carbon in forests like this. On the right, here we show you some of the data that can be collected by multiple robots. And here you see 3 robots simultaneously building maps, obtaining 3 times the coverage in the same period of time. These maps can be easily reconciled and registered. And what you see in these maps is just the location of the trees, their size, their orientation. And this is really the actionable information that's most useful to the timber industry. Well, how do we achieve this today? Well, every one of our robots use inertial measurement units, cameras, and LiDARs. Based on information gathered from these sensors, we compute the required motor speeds to fly this robot to accomplish the task. Well, today, most of the software, certainly much of the architecture we've developed is based on models. Mostly because we understand the models, we know how to fine-tune the algorithms of perception, mapping, planning, and control to achieve the desired outcome. But the holy grail is really to use the data we gather to flights like the ones I just showed you, along with simulation data to directly map our inputs to outputs with an end-to-end learning paradigm, similar to what you see, for example, in text and self-driving. In other words, with enough data and compute, we can create the physical intelligence that's required for autonomous flight. Or can we? This is the big question. Another area we're pursuing is to extend the physical paradigm to heterogeneous teams of flying, walking, and rolling robots in unstructured environments. Imagine having to gather information after a chemical spill in a partially known industrial complex. The mission is not clearly specified. The robots have to infer semantics, figure out what UGVs can do, what UAVs can do. They interact with each other and build a semantic graph on the fly. Again, it happens with little or no prior maps in complex environments based only on language specifications. The system automatically generated grounded subtasks with dependencies, assignments based on robot capabilities, and refines the plan based on feedback. So the overall framework is to go from a specification that's not complete, but a full model of the team, and using LLMs to generate subtasks that are verified for feasibility. And then that's then translated to commands that the robots can execute in parallel, cognizant of the dependencies. As they do that, they update their map and they aggregate this to a common representation. And there's a feedback loop which allows the robots to adapt their plans. Well, there are many questions that immediately arise. The most frequently asked question is, well, models like these are prone to hallucination and attacks. How can you safeguard? So we're also working on something we call RoboGuard. So this is a formalism that allows us to encode safety policies within the LLM so that all plans are grounded in safety. The second question that's asked is, well, if these robots are operating without access to the internet, how do you run such large models on swap-constrained robots, for example, drones? So here we've developed a formalism called PRISM framework that allows us to distill small language models, which then allows the robots to plan to run on device without cloud access. So instead of having a model with hundreds of billions of parameters or trillions of parameters, we now work with parameters, 4 billion parameter models, which function with equal efficiency. So as we think ahead to this field and ask the question, is physical AI hype or reality? The answer is we have some of both. There's a lot of excitement about humanoids, but humanoids have severe power and weight limitations. And in reality, if you look at all the humanoid demos, no practical live demonstrations exist. And of course, we've seen videos of synchronized dancing, and this really doesn't count. Claims of learning leading to dexterity, end-to-end learning leading to dexterity, are a bit far-fetched. Yes, in self-driving cars, we've seen some evidence of that. We've certainly seen this in language and vision, but for physical interactions, this is difficult. So when you see reports with a $5 trillion addressable market for humanoids, we have to question how much of that is reality. I believe most of that is hype. But here's the reality. We don't have a very good understanding of what intelligence is. But for the purpose of physical AI, if you have enough data and enough compute, it translates into something we can call physical intelligence. Of course, we need the right models and the right abstractions. And so this approach using data is not divorced from approach using models. End-to-end learning is not possible as in large language models unless you have some understanding of text, how understanding to encode them, and mathematical models for text. So you need the right models and abstractions. Lastly, I would say for humanoids in particular, but in general for physical AI, we lack the right data sets and the simulators. Thank you all for listening.
Thank you, Professor Kumar, for those insightful perspectives. Next, we're pleased to welcome Professor Antonio Torralba, Massachusetts Institute of Technology. Professor Torralba, we look forward to your remarks.
Thank you. Okay, so I'm going to talk about a slightly different aspect of autonomy, and it's about perception. As we try to build systems that will move around the world and interact with us, we need to think about what is that they are going to perceive. How are they going to perceive the world? And humans, we have a lot of different senses that have the same types of senses. So, I mean, in the last few years, things have evolved amazingly. When I started working in this area, some years ago, around the year 2000, you could take an image like this one here. You could take an algorithm out there and you could ask, what is the content of this image? And it will tell you something like this. And this was the year 2000. It was very difficult to make anything work. But things have changed enormously. And now we have systems that are amazing and that can reason really well. And in particular, we have things like ChatGPT that have kind of addressed the problem of reasoning in a way that is kind of remarkable. And one of the things that was really amazing when ChatGPT started was that people discovered that it was able to solve simple problems. For instance, you could ask it to solve a high school math problem, like here, a treasure hunter found a buried treasure chest filled with gems. There were 175 diamonds, and so on and so on. How many of the gems are in the chest? And ChatGPT just gives you an answer reasoning about all the different mathematical equations, what are the unknowns, and at the end it will tell you the actual number of gems that are on the chest, which happens to be wrong, but it's just perfectly reasoned, just amazing. And so, here it wasn't able to actually find the right answer, but ChatGPT, people discovered that it has a lot of other different aspects that allow, to build systems that actually can perform really well complex reasoning tasks. For instance, you could, every time that you ask ChatGPT one question, it will answer a different thing, even if it is the same question with the same words. So here, when we asked this particular high school math problem, the first time it got it wrong. But two students at MIT discovered that the second time that you ask the same question, it just happens to be right, and it's just by luck. So now you have these two different answers. You can take the second answer and you can go to the first LLM, to the first window in which you were asking ChatGPT this question, and you can say, wait, just a different instance of you answers something different, and you just copy paste the answer that it gave you, and then you ask, what do you think now? And it changes its answer, and it agrees with the second one that the right answer is the other one. And you can do the same thing with second ChatGPT, and now you give it the wrong answer that was given by the first one, and you say, what do you think now? And if you do that, it actually keeps the right answer. It does not get fooled. So that was showing that these systems, it's just amazing how you can actually make them reason in different ways. And this reasoning field has exploded since. So we started trying to build vision systems and perceptual systems, and suddenly what seemed to work really well is the systems that can reason through language and solve very sophisticated problems in a way that was kind of unexpected. And the field has exploded, and we have all kinds of systems out there. For instance, another amazing thing that happened just a couple of years ago is these generative models for video generation. The one that I'm showing here is from OpenAI, is the system called Sora. And what you see here is a movie that was just generated by one of the systems, by Sora, by responding to a particular prompt. So this is a synthetic movie. So these systems are really amazing. And, generative AI in particular has been showing remarkable results. For instance, here a neural network is trained to generate images, and the way that it does it is to take a random vector where you can think of each number, each component of this vector being just like throwing a dice and just recording the number that you have. And so it's just going to be a collection of random numbers, and the neural network learns to transform that set of random vectors or random numbers into a picture. And if you want to generate a different picture, you just take a different random vector and a different picture appears, and so on and so on. So when these generative models for images were introduced, it was just really amazing, the fact that they were capable of doing something like that. So as we build these systems that are very sophisticated, one of the problems that we face is how can we trust them? How can we understand what are they actually doing? So one of the goals that we have in my group and many other labs doing research on trying to understand what is happening inside these neural networks consists on the following. We try to understand what is the meaning of the representation that the neural network has learned. The neural network is composed of many different neurons. Some of them might have learned to perform particular tasks that maybe we didn't actually specify them in advance. We only have the final goal that we want to accomplish, like generating an image, but maybe something inside the neural network is happening that derives meaning that we were not defining beforehand. So for instance, in the case of image generation, one of the questions that we had is, what are these units learning? Are there units that have learned to draw towers and trees and doors? And even though we never actually taught them to do that, we only teach them to generate a full image, but are there units that are specifically tuned to generate specific parts of the image? And what we discovered is that if you look inside the neural network, in a big neural network, well, it happens that in layer 4 in that neural network, the neuron 84 is selective to windows. Whenever that unit is activated, a window appears on the image. And there is another unit, 315, that whenever that unit is activated, a chair appears on the picture. So it's like some units have learned to draw, to generate specific parts of the image, and they have discovered these concepts, even though this neural network was only taught to generate images, and we never explained to a neuron, to the neural network, what is a chair or a table or a window. It just saw images in general. And you can actually start doing interesting things. For instance, you can take an image that was generated by the neural network, and now you can take the units that are responsible of drawing windows, and you just remove them, and the windows go away, and the only thing that appears is the walls and paintings. But this concept, now this unit, this neural network has lost the ability of drawing windows. You can do other operations. For instance, here is an image that was generated by the neural network, and we discovered that there are some units that are responsible of drawing grass, and you can just activate the grass units everywhere on the image, and then suddenly grass appears in many different places as if humanity was gone for a long time. So these neural networks are actually learning meaningful representations. They look in many cases like black boxes, but it's possible to open that black box and try to understand what the representation is learning. But we have made a lot of advances in vision, but what about the other senses? Because the other senses are just as important. In fact, for instance, there is another sense that for humans is just as important as vision itself, which is touch, the sense of touch, tactile sensing. In our brain, just around 30% of our brain is devoted to vision. Well, around 10% of the brain is devoted to tactile sensing, which is still a pretty significant portion of the brain. And yet, advances in the technology to record the signal related to touch is just in its infancy. We have amazing cameras. Vision research and the discovery and building cameras has a history of more than 150 years. Tactile sensing is just starting. And yet for us, it's super important. It's a very important sense, and we just don't have the technology. So how do we build tactile sensors? Well, there are a number of efforts in our group. We are trying to build, in collaboration with another professor at MIT, Wojtek Matusik, we are trying to build simple tactile sensors that put pixels in the hand and different parts of the body in order to record tactile signals. There are other faculty like Ted Adelson with a project that he calls GelSight that also builds sensors for recording tactile signals. So, the way that the sensors work is just, in this case, it's just a glove that allows you to put in the hand of a human, but you can think of also having this to be part of, being on a hand of a robot. And it's basically like sensitive skin that you can wear. And as you touch objects, it records the pressure that you apply in different portions of the hand. So here I'm showing you a movie showing the different signals recorded by the glove. But things get very interesting when you have this type of signals. If you have them in the hands, it's very interesting for interactions, but if you have them in the entire body, they become very interesting for many different tasks. So for instance, what happens if you put even pixels in your feet? What happens if you put tactile sensing in your feet? Well, it happens that you can have a pretty good picture of what the foot is doing in contact with the ground. And just from that information, just by recording the pressure that you apply to the floor, you can actually infer the whole body pose of the person. Without a camera, just by recording the pressure on the feet, you can actually build a pretty good estimate. You can get a pretty good estimate of the pose of the entire body of the person. So this, it feels like a very important type of signal for robotics in general. So, as we build autonomous systems, we need to think about the perception. How do we build stronger perceptual systems? And we have a lot of senses. We have very good visual systems. We have very good artificial auditory systems, but we lack all the others. We lack the touch, we lack a smell, and we lack taste. And a lot of more progress will be needed here. So with that, thank you so much.
Thank you, Professor Torralba, for that engaging presentation. Now, we are delighted to welcome our special guest, Associate Professor Minh-Triet Tran, University of Science, Vietnam National University, Ho Chi Minh City. Associate, to your remarks.
Good morning, everyone. And today it is my great pleasure to give a talk on the future of intelligent health science. And I would like to tell about the future where modern medicines, artificial intelligence, together with the smart interaction and traditional medical wisdom can come together. And in particular, we focus on new concept of AI agents, an intelligent system that can observe, learn, reason, and give advice to doctors as well as patients. If we look at the healthcare today, it is most reactive. We wait until we feel unwell and then we go to the doctor. That means that we often detect diseases late, and in the future, this will change. Healthcare will become continuous. AI agent will help us to monitor our health quietly in the background, and they will detect early signs of risk and help us act before disease develops. So instead of treating illness, we focus on maintaining health. This transformation is built on 5 key pillars: connected data, and AI is a co-pilot, interactive intelligence, digital twins, and responsible AI. But more importantly, these pillars are connected through AI agents. These agents are not just tools to give outputs. They are systems that can continuously observe data, understand the context, make suggestions, and even take actions when needed. We can collect the data from different sources. We have clinical record in hospital, imaging data like CT or MRI scans, wearable data such as heart rate or sleep patterns, or even we can use the device Professor Antonio already mentioned as the sensors in the feet of the patient to collect continuous sensors from them every day at any time. And each of these data sources tells part of the story about our life, our health. Healthcare system today are under significant pressure. We can see here there is an explosion of data far more than human can process alone. Second, clinical decisions are becoming more complex, especially with new treatments and technologies. And thirdly, patients expect personalized care tailored to their unique condition. So our agents help address all 3 challenges by analyzing data at scale, supporting decision-making, and adapting to individual needs. However, in current reality is that data is still fragmented. A patient's medical history may be in different hospitals, a lab results in other system, or wearable data on different personal devices. And doctors often need to manually gather and interpret all this information. And we can ask AI agents can act as intelligent coordinators and collectors. They can automatically collect, organize, and summarize data to help us a unified view that can help the doctor in designing for the final decision. In the future, we will have a unified model system. AI agents will sit as the center of the system and connecting all data sources. Let's look at this example. An AI agent can monitor heart rate from a smartwatch, ECG signals, blood pressure, activities level, and even for medical history. And by combining all these signals, it can help us to estimate the risk of heart diseases dynamically and detect the abnormal patterns. It can alert in both patient and doctor early and can preventing for heart attack. Not only for personalized use, we can use AI agent for operating at larger scale by analyzing data across many individuals. We can use AI agent to detect trends and predict outbreaks. For example, they can identify the early sign of flu spreading in a community. And at this point, a very important question often comes up: will AI replace doctors in future? And I think the answer is no. AI agents are designed as a co-pilot, not replacement. Think of AI as an intelligent assistant. It can process large amounts of data, detect patterns, and suggest possible diagnoses or treatments, but it does not have human experience, empathy, and ethical judgment. So doctor remain the final decision maker in this case. To understand how AI agents helped in healthcare, we can think of four main capabilities: foresee, think, act, and create. First, they can see, yes. For example, they can analyze medical images such as X-ray or CT scans and detect anomaly in the very hard cases. Second, they can think, they can act, they can automatically routine tasks like scheduling, reporting, or monitoring a patient. And fourth, they can create. They help design new drugs or generate treatment plans. And let's look at how AI agents support doctors in daily workflows. In many hospitals and in Vietnam as well, doctors need to review hundreds of medical images every day, very hard workload. And this is time consuming and can lead to very time consuming and effort. An AI agent can pre-analyze these images and highlight the suspicious regions. For example, they can mark areas that may indicate tumors or lesions. And another major challenge in healthcare is administrative work. Doctors often spend a lot of time writing reports, updating records, or handling paperwork. And use AI agent can help by listening to doctor-patient conversation and automatically generating structured notes. They can also summarize patient history or organize the lab results. AI agents can be used in helping us develop new medicines. Traditionally, drug discovery takes many years and costs a lot of money. Now we can use AI tools to analyze large chemical data sets and predict which compounds are likely to work. In the past, AI systems were more passive. They took input and give output. But now we can moving forward to interactive intelligence. We can communicate with users through chatbots or some kind of agents, ask questions and explain their reasoning. And this shift is very important because healthcare is not just about data, it is about understanding, trust, and collaboration. For AI agent to be used in healthcare, they must have several key abilities. They must communicate clearly with doctors and patients as well. They must explain their reasoning, and they must adapt based on the feedback. And finally, they may collaborate effectively between humans, becoming a true partner rather than just a tool. And one very important thing is natural language interaction. Doctor can simply ask questions in normal language, such as, what evidence support this conclusion? And AI agent can respond with suggestion, explanation, or supporting data. An AI agent is not limited to hospital. They can also support people in daily lives at any time, at anywhere. And a personal health agent can monitor our activities, sleep, and different kind of signs. For example, I just say, I feel tired today, and the agent can analyze the recent data and suggest possible reasons, such as lack of sleep or high stress in daily activities. So finally, we move toward a model to share decision making. In the future, decisions are not made by the doctor alone, but we can have the AI to support them. Not AI alone, not doctor alone, but they have the collaboration. AI agents help explain complex medical information in simple terms so patients can understand the options. This also allows patients to participate in more actively in their care, leading to better outcomes and higher satisfaction. And digital twin is very important idea. A digital twin is a virtual model of a patient body that evolves over time, not static, but continuously learns from the data such as medical records, wearable signals, and lifestyle behavior. And in this case, we can get information accurately and all the time so that doctor can make the good decision for treatment. And this leads to a major shift in healthcare. Traditionally, we wait for symptoms and treat diseases, but now we move toward predictive and preventive healthcare. And To build such a system with a strong data foundation, this includes many types of data such as clinical records, imaging data, wearable sensors, and so on. And we can create multi-dimensional view of health instead of isolated measurement. And with continuous monitoring, AI agents can detect subtle changes that humans may not notice. And all of this leads to the precision medicine. Instead of treatment patients based on the general guideline, we treat each patient based on their unique data. And it is very, very important for trust and responsibility in this case. We really need the rigorous testing, clinical validation, and clear communication of limitation. And AI should support decisions, but not make them blindly. And we need the privacy protection. We need to consider for federated learning, data encryption, or local processing to keep the data utility and privacy protection. And doctors must understand AI if we have the explanation to them. And they should have why the suggestion is made and what data supports it and what uncertainties still exist in the decision or suggestion. So we go to a very important idea I would like to share in my talk today is how we can employ the traditional medicine perspective. Traditional medicine, or even we call Đông y, offers a very different perspective of health. It focuses on balance, harmony, and long-term well-being. We consider for the concept of yin and yang balance, for the energy flow and organ system relationships. And this provides a holistic view of health that modern medicine sometimes overlook. So we need to bridge two worlds. For example, modern medicine provides measurable data, while we use the traditional medicine to provide holistic interpretation. So by combining both, we can achieve a more complete understanding of health. And making more objective diagnosis, in this case, we can base on the information of the color of the tongue or the shape of the tongue, or even we have other signal to get the final decision. An AI agent can also enhance herbal medicine by identifying active compounds in herbs, analyze interactions between herbs, or predict potential side effects in this case. Now we can take one further step, integrative digital twin. This model includes the Western biomedical data or Eastern indicator, and also lifestyle and environmental data. And we integrate all of this into a one unified model. And finally, in conclusion, the future of healthcare is not just about technology, it is about integration. By combining modern medicine, traditional knowledge, intelligent AI agents, we can create a system that is personalized, preventive, holistic, and human-centered. In the future, AI does not replace the doctors. It empowers them, and it helps patients live healthier, longer, and more balanced lives. Thank you very much for your attention.
Thank you so much, Associate Professor Minh-Triet Tran, for sharing your expertise with us. And now, to wrap up our discussion, I'd like to invite our panelists to join us for a brief panel discussion. This will be a 15-minute session where they can share any final thoughts or insights before we transition to the Q&A portion of our webinar. Please note that Professor Vijay Kumar had a prior commitment and is unfortunately unable to stay with us for the panel discussion and Q&A portion. But we sincerely thank you and appreciate him for joining us earlier and sharing his insights. And now it's time for the panel discussion. I'd like to take the floor back to our chair. Professor Daniela Rus, the floor is yours.
Well, thank you so much for three amazing presentations. And you have given us the state of the art in so many interesting ways. Vijay has explained to us the state of the art in physical autonomy. And Antonio has explained to us the state of the art in perception, which is necessary for agents that operate in the digital world and in the physical world. And then finally, we had the Minh-Triet talk about how agentic AI can help in healthcare, can impact healthcare. And what I'd like to observe at the beginning is that we have different kinds of AIs that are all coming together. And for those of you who are new to the field of AI, I want to explain that there is predictive AI, which takes data and aims to tell us what has happened in the data or what might happen in the future. Generative AI is about training on existing data, but producing entirely new content. And then we have this new field of agentic AI, which is about creating not just a static answer, which is what we get from predictive AI and from generative AI, but we get a dynamic answer. We get almost like a project that has multiple steps, and these steps can be involved in a digital type application or in a physical application. And these technologies together are becoming extraordinary. So I would like to ask Antonio and Minh-Triet their thoughts on the convergence between large language models that are now connected to robot bodies, to vision systems which are becoming multimodal, and we're also beginning to see AI that is moving from the screens into the physical world on the body of the robot. And so, what do you think are the hardest unsolved problems to get AI work reliably in the real world outside of the lab? And this could be on a farm, in a warehouse, in a hospital, whatever application you would like to associate with the physical world.
Yeah, so I can start. I think there's been so much advances in everything that is related to agents in the digital world. However, once you have to go to the physical world, as you know very well, things get really difficult. And I think it's like somehow, it's been pretty amazing to see all these advances on reasoning and vision and language models, but we haven't really seen, a similar revolution yet on the physical world. And I think it's about to come, but I think, and I'm not talking about developing like better vision language action models that can actually reason about actions in the world. I actually mean about the mechanical pieces, the hardware, all the things that actually make, that at the end is the thing that is going to really interact with the world, is the physical hardware. And I think that if you think of a lot of the advances in AI now is by getting closer to a degree on how the human brain works with neurons and so on. It's still pretty far away. I mean, pretty far away from how biology actually implements intelligence, but there is a step. But I think that the way that we build mechanical bodies still very different from how nature does it. And I know that there is a lot of work on soft robotics and so on, trying to get a little bit closer, but I feel like that's the thing that is really missing, that is still very difficult.
Antonio, that's really an important observation because when it comes to physical agents operating in the physical world, it's very important to remember that each of these agents has a body and the brain. And the body defines the capabilities of the machine. And then the brain drives the body to deliver on those capabilities. Now, Vijay told us that we have seen a great price performance decrease in sensors and in motors and generally in the hardware platforms that we use to build machine bodies. But we continue to build robot bodies out of metals and hard plastics. And so these are very rigid materials. Whereas when we look at nature, nature has built-in compliance. It has built-in ability to respond to uncertainty. Nature is built quite differently from how we engineer today's machines. And so we see great progress in soft robotics. Some of the most advanced research aims to combine biological tissue with silicon-based tissue to create systems that are controllable yet in some sense closer to nature so that we can capture some of the properties, but we're still quite far away from many points of view. We're far away from the point of view of sensors. So we don't have skin yet. I mean, the gloves, the sensors that are built at MIT and at other very forward-looking organizations around the world are still not skin-like sensing. So this is actually necessary for anything that interacts and manipulates the world at a level of dexterity comparable to the human interaction. And so we need that. We've made a lot of progress on cameras, but we do need better cameras. We need much faster cameras and faster perception actuation loops for manipulation, because the speed at which the egg you're holding will drop if you're not holding that egg strongly enough is much faster than what we can do now with our reasoning models. So all of that is very, very important. Then also the motors, the actuators have to get better, have to get more dexterous. So the body remains important if you have a machine that interacts in the physical world. But I would say that also the brain is important. And just to add to what you said, Antonio, right now the models, the AI models that are most capable are actually huge models that are stored in the cloud. Now, imagine being a self-driving car driving at 60 miles an hour and waiting for the cloud to tell you what to do, right? I mean, the danger of an accident is imminent. And so I think that for physical AI to get better, also the AI models have to get better. They have to be better at understanding physics and understanding the world around them. So so these are all very important points. Let's see. Minh-Triet, we kind of took over with robots, but let me turn it over to you so you can add about the physical world and maybe about the healthcare domain.
Yeah, in the case for the AI and physical AI to be applied in healthcare services, we think that we can develop things that can help the people in practicing different exercises in hospital as well. And we can have some robots in order to help patients in different activities. However, in order to do that, we also have extra difficulties. First, they must deal with patient that are in illness, and we need to carefully care for them. The next thing is that it is very important for the data we collect to train our robots for interaction in this case. In that case, patient is quite fragile. We need the information and integration of the decision making into the robot in that case. Currently, I think we can develop chatbots or something like humanoid robot in order to chat with a patient just to welcome them in hospital, and some hospital in Vietnam also develop such system already. But I think in the future, if we need some dedicated robots in order to interact with patient, or it can help doctors in operation, I think it does take time. And we need more information to train, more environment to test, and also we need the adoption of people to use the technology in the real environment. Yeah, I think so.
So let me stay on this topic, and maybe I have separate questions for each of you. So Antonio, you've argued that machines still lack the visual intelligence that humans take for granted, and your recent research explores whether AI can learn visual understanding from much simpler data than we currently use. Now, if that succeeds, what does that unlock for AI? And especially, what does it unlock for AI in the kind of resource constrained settings that we have with physical AI and physical AI applications?
Yeah, I think that right now the reliance on massive data sets for learning, it creates, it has created lots of new opportunities, but it also creates a number of challenges, and it has made us addicted to that, to having access to very large data sets. But in many cases, you also need to be able to learn on the fly. You need to be able to learn new things that you haven't seen before. You have very few examples. And of course, you have all this additional knowledge that is helping you to learn from these very few examples something new. But it's important to continue developing techniques and understanding how do you learn from little data. So one of the things that we try to do is to try to understand what is in the data. So when you train a model with a lot of data, the model is not necessarily extracting from all that data information that is very sophisticated. It's actually trying to extract the essence of that data in order to learn something. The question is, can we capture that essence in a way that we can teach a system with very little data, but that just happens to capture that essence, so that the system starts being somewhat good. It's not going to be as good as if you were training it with a lot of data, but it will be somewhat good just by having trained with that small amount of data. And in this particular case, the data is it's not like you're picking some examples that are good or not. It's trying to extract from, trying to understand what is like the properties of the data that are actually important for learning. And so that's I think that is kind of more fundamental research, trying to understand, what is in the data that is useful for learning.
Antonio, I want to have a quick follow-up on that. Not many AI models are provably causal. So I wonder, what is the role of causality in the kind of learning that you are advocating?
Yeah, it's unclear, what the role of causality. In some cases, one thinks that causality is very important. I think that if you're trying to build AI systems, so in the work that we do, I don't think that causality plays necessarily an important role. But I think that if you're trying to develop systems that will have applications for AI for science, I think that in that case, then thinking about causality is really important. If you're trying to build systems that are autonomous systems that react to things in the world, sometimes correlations are very useful. And to have exact causal understanding of the world is not necessarily essential. Or at least I will say that it's not clear whether it's essential or not. Correlations might actually, take you a long way towards a workable solution without necessarily understanding perfectly the causal relationships in the world. Like I think that, for instance, humanity hasn't really been hasn't really understand causality, the cause of different phenomena that happen in the world for a very long time, and we were perfectly functional. Like physics, we didn't really understood physics very well for a long time, for millions of years, and yet humans were able to do all kinds of things. So you have maybe some intuitive causal analysis in your head, maybe it's not conscious, but it's unclear whether that's really causal analysis or just like strong correlations that might be just predictive.
So, Antonio, I think we can discuss this quite for much longer, but let me pause and turn to Minh-Triet, because I would like to ask you a question about your healthcare research, which shows what's possible when we can create a digital twin and use that for health assessment and diagnosis and predictions. So here's the question: as AI models get more capable, do you see a future where intelligence can become distributed across many small agents that coordinate rather than the current state where you have one expansive model that captures everything? And what does that mean for the kinds of systems, for the kind of agentic systems that we will need to create? What does that mean for how we support the agents to interact with each other?
Thank you for your question. I think we try gradually to gather information from different sources, and we process and try to represent them in a way that computer can understand, can process, and get the inference from that. However, we can also try to process the history of the patient or regular people so that we can predict something happen in the future as well as an extra information for our system. But in order to do that, we need also the simulation to predict something. For example, if the elder people, they cannot move easily in the flat region, we can also predict they can fall in some scenario if they move walking upstairs or downstairs or something like that. But we cannot perform the experiment. We need some simulation model and use the physical information to simulate such thing and predict what can happen if they do some action in real condition. So by creating a digital twin and integrating more and more information, even from the daily activities of the user or the patient, we can understand more about their habits, about their way of living or things like that. That is the information we have the copy of the real people. But in order to do that, we can think about a very expensive AI system in order to give guidance. And actually, people do not want to share their personal information to the whole system like that. They tend to keep their own personal information in maybe their mobile devices or in some secret location. So I think in that case, we try to have the decentralized mechanism for have different small agent just to process and provide enough information for our agent in order to get the conclusion. But how to do that? We need the interaction. And it is not only the work for AI engineer, for scientists, but we need for the solution from software architecture and the network for communication. We have so many wearable devices, smartwatch or other kinds of devices, but how we can get the data to be sent to the mobile device to capture information from smartwatch or other kinds of devices like that, and how we can get the continuous information to be transmitted successfully, Bluetooth or something like that. So we need the technology in order to keep the connection smoothly and to distribute the operation to different sensors and devices. But I think we need the technology for implementation, and we need the algorithm for integrating different sources of information from devices. Yeah.
So let me ask one more question before we turn over to to the Q&A session with the audience. And so here's the question. There is recent work on understanding what neural networks actually learn that has revealed surprising gaps between what the systems appear to know and what they actually understand. And as we give AI agents more autonomy, as we ask AI agents to do things for us, whether in the physical world or in the digital world, how worried should we be about the gap between performance and genuine understanding? Is interpretability a prerequisite for trust in safety critical systems, for example, in healthcare? Antonio and Minh-Triet, what do you think about this?
Do you want to start, Min?
Yeah.
Minh-Triet, do you want to start?
Okay. I think especially for the healthcare service, it is very, very important for establishing trust and also for responsibility in this case. The first is the transparency in building trust for healthcare system. Let's say, if users think they're talking to human when it is actually AI, this can be some misleading or manipulative. So we need the clear disclosure, something like this is an AI assistant, I am AI assistant, to help users to interpret the responses correctly, avoid over trusting the system and feel respected rather than be tricked. The next one is that the users need context to make safe decision. Otherwise, they will rely too heavily on the information provided by only the AI and make the medical or financial or legal decisions just based on incomplete or incorrect outputs. So the key point is here is a disclosure enables informed judgment, reducing the real-world risk. And finally, we also need the responsibility in designing, not just disclaimer. We have the ethical responsibility as continuous, visible, and honest design, not as a hidden fine print in this case. AI assistant labels should be used, explain the capability and also the limits, and also easy access to human support when needed in this case. Yeah, I think something for AI to be trusted for healthcare like this. Yeah.
Antonio, would you like to add?
Yeah, and I think that at some point, I think that one thing that is interesting on explainability is just trying to understand what is happening inside these neural networks. I think that just the science of it is really interesting. Just like neuroscientists try to understand how the brain works. It's not like we can actually explain what we do and how we take, we make the decisions that we make. We can give you kind of explanations, but are not really true descriptions of our process, our mental processes that took place in order to make decisions. So neuroscientists are trying to open the brain and understand what's happening actually there. But I think that at the end, performance is going to be very important. Like you can have some explanation, some level of description of what is happening. It doesn't need to be very detailed, but some level of description that is predictive of errors, and then performance is kind of going to be the main driver of trust.
Amazing. So I think we should switch back to our moderator who will moderate the questions from the audience. Or would you like me to moderate the questions from the audience? I see some questions in the chat, but not a lot.
Professor Daniela Rus, we continue to the Q&A session. And before that, a heartfelt thank you to our panelists for their invaluable contributions today. While they take a well-deserved 5 minutes, we would like to share that the VinFuture Prize is accepting nominations for the 2026 award season. We now invite you to watch a short video tutorial on submitting nominations for the 2026 VinFuture Prize. Please keep an eye for the video, and we'll be back shortly for the Q&A session.
Greetings from the VinFuture Prize. Please find instructions for the nominator following these steps. To begin, you can access the nomination portal at online.vinfutureprize.org/nomination. Alternatively, you can scan the QR code on the screen to open the nomination webpage. On this webpage, you can download the instructions and the endorsement letter template. In the instructions, you will find the complete nomination form where you can draft the nomination at your convenience. Afterwards, you can copy and paste draft into the online portal. Please click on Sign Up, and upon successful registration, you can simply use your ID and password to log in. After logging in, please click here to start a new nomination form. Subsequently, you can see 7 content tabs on the nomination form to begin the nomination process. On the first tab, please select the prize category as well as the type of nominee, whether it is an individual or a group of nominees. Then, click the Start button to proceed to the second tab. And we would like to draw your attention to tab number 5 and tab number 7. On tab number 5, your evaluation, you are invited to give your evaluation of the nominee's invention, including its groundbreaking discovery, scientific fundamental knowledge, specific approach, uniqueness, and advancement. Additionally, you are required to clarify if the invention can be transferred to a product and highlight its most significant socioeconomic impacts. This includes the number of beneficiaries, such as people, countries, and continents. Please explain how you believe this invention has or will potentially transform the everyday lives of millions, if not billions, of people. Next, please provide information on the history of the invention, such as when and how it started, and who else, except the nominee or nominees, was involved in initiating or contributing to the invention. About tab number 7, supporting documentation and evidence. There are several important documents that the nomination portal and form require. We would like to draw your attention to 3 critical items. The first one is the CV of your nominee, or the CVs of your group of nominees if you are nominating a group of people. The second important item is the endorsement letter. 3 endorsement letters are strongly encouraged, but 1 is mandatory. The third one is the additional form of nominees. Please provide as specific information as possible. Additionally, you are strongly encouraged to include any valid intellectual properties, publications, patents, or other supporting documents that provide evidence for the nomination. Finally, after filling out and providing all the content in the 7 tabs, please click on the Submit button at the bottom of the page to submit your nomination.
Ladies and gentlemen, we encourage you to submit your valuable nominations for the 2026 VinFuture Prize before the deadline of 2 p.m. the 17th April 2026 Vietnam time, GMT+7, by visiting our website at the link online.vinfuture.org/nomination plus or scanning the QR code below. Your participation is greatly appreciated, and we thank you in advance for your valuable contributions. Additionally, please keep in mind that as part of our nominator recognition program, 5 outstanding nominators will be selected to attend the VinFuture SciTech Week with all expenses covered by the foundation. And now, the moment we have been waiting for, the Q&A session. It's your chance to delve deeper with our esteemed panelists, Professor Daniela Rus, Professor Antonio Torralba, Associate Professor Minh-Triet Tran. Please feel free to actively participate in our discussion by using the raise hand function. We'll unmute you for a direct exchange with our panelists. For those who prefer a more indirect approach, we encourage you to use the chat box. Simply type your question, and we'll ensure that read the most relevant panelists within our time frame. Don't hesitate. This is your opportunity to gain valuable insights from these leading experts. As Professor Daniela Rus mentioned, we received a lot of questions, and the first one is for you, Professor Daniela Rus. The question is from Dr. Durga Gangisetti from George Washington University. Your question is, In robotics and autonomous systems, safety often requires architectural constraints rather than dust-based models. What architectural patterns do you think will be necessary to ensure that the autonomous AI agents remain comfortable and aligned when interacting with real-world systems? Please, Professor Daniela Rus.
So, let's see. I feel like as AI agents get better at making plans and taking actions over long stretches of time, the goal shouldn't be to stop autonomy, but to kind of bound it, to define guardrails, to let agents, whether physical or digital agents, to really clearly understand what they can and what they cannot do. And I would say that for low risk uses, the guardrails could be looser for safety critical high risk uses. We really have to have stronger checks before and during deployment. And so technically, I would say that the most reliable safeguards look a lot like the way we secure modern software systems. And so instead of giving an agent broad access to everything, we give the agent limited permission, and we give the agent only the tools it needs and for the tasks that it's authorized to do. And so that's one practical way of approaching this challenge. Another one is to trust but verify. In other words, to build a solution and then to apply safety and verification tools to ensure that the solution is going to behave correctly in your circumstance, in your application.
Thank you so much for the response. And we got a question for Associate Professor Minh-Triet Tran. This question is from Professor Hồng Bùi from Vin University. She was so inspired by what you share and feel positive about about the healthcare future. Your question is, have you ever thought about how to collect all the data sources that you were mentioned in your talk? Please, Professor.
Yes, thank you very much for the very interesting question. First, we need the information to be collected in hospital, and maybe at VinUni, where Professor Hombui is currently working. I know that in VinUni, there are collaboration between the Smart Health Center with at my hospital to collect the information for heart stroke diseases. And of course, in order to do that, we need to collect different kinds of patient information. In Ho Chi Minh City, we also have the collaboration with different hospital as Thống Nhất Hospital or Bệnh viện Y học cổ truyền, traditional medicine hospital. And of course, the first thing is try to process data, history of the patient into what kind of information representation that we can process automatically in the system and understand in natural language as well. Besides, we also need to collect the information for the activities we perform daily at any time, at anywhere. Apart from the commercialized wearable devices as smartwatches, it is very interesting for developing new kind of the wearable devices, or even we can use the surveillance cameras to monitor activities of people, especially for elder people at any time in the house or in the environment. In that case, we can have the better view of different activities, but how to collect and how to consider for the privacy of the patient is the question we need to answer to process that. Yeah.
Thank you so much for your remarks. And now it's question for Professor Antonio Torralba from Dr. Pei Faculty of Computer Science and Information Technology, University Malaysia Sarawak. Your question is, how would you approach the issue If patients not using formal language structure or even indigenous languages when communicating with AI chatbot in healthcare industry.
I'm not sure I understood the question. Could you repeat, please?
Can you repeat the question?
Okay, Professor, your question is, how would you approach the issue if patient not using formal language structure or even indigenous languages when communicating with AI chatbot in healthcare industry?
So I think it's the question is about
Yeah,
multi-language
Yeah.
yeah,
interactions.
yeah. And in particular, I guess it's about indigenous languages also that might be rare. Um, I mean, it's interesting that these systems seem to be fairly good at understanding even languages that didn't have a lot of training data. But one surprising phenomena that happens in these models is that the reasoning capabilities seems to be connected to the language that you communicate with. So um, if the language that you're using to ask questions to this system is not a language that for which they had a lot of training data,
Yeah.
even if the system understands, it might actually be, it might actually give you the wrong answer just because it doesn't have the right reasoning capabilities, because it hasn't learned enough. So this is different from how humans work, no? That you hear something in one language and then you might kind of translate it to your own mother tongue or something and then reason there. These models seem to be mixing reasoning and language capabilities. So uh, I think that that's still one thing probably that needs to get better, to get a better separation of the reasoning mechanisms and the language. Uh,
Thank you so much, Professor Torralba. AI was always a hot topic, and we received a lot of questions from our esteemed participants. But now the time for Q&A session comes to an end. So we hope to discuss further with you in the future. And now, as we wrap up today's enlightening InnovaTalk webinar, we extend our heartfelt thanks to our esteemed speakers, Professor Daniela Rus, Professor Antonio Torralba, Professor Vijay Kumar, and Associate Professor Minh-Triet Tran. We also extend our sincere appreciation to the MIT Computer Science and Artificial Intelligence Laboratory for their invaluable partnership in co-hosting this important dialogue. To audience, thank you for your active engagement and thoughtful questions. And please remember that the VinFuture Prize is accepting nominations for the 2026 award season. We encourage you to submit your valuable nominations before the deadline of 2 p.m. the 17th April 2026 Vietnam time GMT+7 by visiting our website at the link online.vinfuture.org/nomination or scanning the QR code below. Your participation is greatly appreciated, and we thank you in advance for your valuable contributions. Additionally, please keep in mind that, as part of our nominator recognition program, 5 outstanding nominators will be selected to attend the VinFuture SciTech Week with all expenses covered by the Foundation. Thank you once again for joining us today. We look forward to welcoming to the future InnovaTalk because we continue to explore innovations that serve humanity. Until then, best wishes to all, and we hope to see you in our next event.